is a distinction between a quantum computer and a computer based on flipping coins. And this distinction is a phenomenon called entanglement. For example, 2 of 4 oracle types introduced in the previous lecture use this entangling operator C0. And we cannot implement C0 on the flipping coins. Honestly, it's not easy to implement even on quantum particles. But with small number of qubits, 2 to be exact, we can do it. It's not much we can compute with 2 qubits, but at least we can demonstrate the action of David Deutsch's algorithm. So the main idea here is that we are going to entangle qubits that are carried by different quantum properties of one particle, photon in our case. You remember that under some circumstances, photon can take 2 paths, and this position of photon in interferometer can encode 1 qubit for us. And another useful characteristic of photon is its polarization. And it can encode another qubit, the second qubit, and these 2 characteristics, position and polarization, we are able to entangle. So this is it, our real quantum computer with 2 qubits. The main part of it is here. It is the Mach-Zehnder interferometer, which consists of 2 semi-transparent mirrors and 2 ordinary mirrors. The whole thing is settled on a heavy and flat chipboard. The real interferometers, they are usually based on some surfaces made of cast iron, because the Mach-Zehnder interferometer is a device very sensitive to the slightest vibrations and slightest deformations of this basement, because it causes the change of path length inside the interferometer. But since we are doing everything ourselves, chipboard works for us. It is heavy enough and it is flat enough. The source of photons is here, this simple laser pointer, red light, 650 nanometers, and 100 milliwatts. To polarize the photons, we use this linear polarizer we already met before in this course. And the beam splitters here are implemented as beam splitting cubes, non-polarizing, and best performance on the red light. The oracle will be implemented as these 2 half-wave plates. And we can see the interference picture there on the screen. And the pattern of this interference will show us the result. We will read our result of our computation by this pattern. On this slide, you can see the top view of our quantum computer. So the laser is here and emits photons of this wavelength, and then a photon goes through this polarizer and it reaches the beam splitter. And you can see here on this picture the position of semi-transparent surfaces of these beam splitters, which are here. And now, if you don't want to buy these beam splitters, you can find one in old photo cameras. They are used there to divide the beam of light, which goes to the camera, to the film, the beam splitter here, and to the eye of a photographer. Now, if your old camera looks like this, so here's a small window for the light which goes to your eye, then probably there's no beam splitter. But if there's no such window, then probably the beam splitter, it must be there. Okay, now these beam splitters, they split the photon in two ways, and it is ready now to reflect from these ordinary mirrors. Now, these mirrors are not exactly ordinary. They must not have a glass surface on them, because the mirror which has a glass surface, like this, has two reflection surfaces. One is glass, and another is the mirror itself. And this small delay, this small change of wavelength allows this photon to interfere, and this interference can overshadow the interference from the different paths in interferometer. So we need mirrors without this glass here. This type of mirrors are usually used by dentists for some reason, and I suppose that if a mirror with a glass breaks inside someone's mouth, it is worse than if there is no glass. So you can easily buy mirrors without the glass. You just need to pretend to be a dentist. Okay, and we have now these two paths inside the interferometer. The photon reflects from here and reaches the second beam splitter, where it goes here. This photon reflects, goes here, and it goes through also. And this photon goes through and reflects. And here we can place the screens to see the interference of the photon from these two ways. And now the type of this interference will tell us what is inside of this interferometer. And the most important thing here is these wave plates, which will represent an oracle to us. Let's learn how wave plates work. I already told you about crystals which have an optical axis. For example, polarizers from the previous week, they have optical axis, and the photons polarized along this axis pass it through this crystal, and the orthogonal photons, they were stopped by this crystal. Now, the wave plates are also crystals with optical axis, and again, photons polarized along this axis pass through this crystal without any trouble. And this axis is often marked as fast. You can see it here. And it forms the ordinary beam. Now, the photons that are polarized orthogonal to this fast axis, they also pass through wave plate, but they experience a little delay in this process. This is why these wave plates are often called the retarders, from French retardé. Okay, now the delay, which experiences a photon polarized orthogonal to the wave plate's axis, depends on the thickness of the crystal. And we can fit this thickness, so the delay would be half wavelength. And in this case, this would be half wave plate. And the photons polarized orthogonal to the fast axis produce the extraordinary beam, not only in half wave plates, but in any wave plates. Okay, now let's see what happens to a photon which is polarized not orthogonally, not along this axis, but something like this. So this is our polarization of photon. Since the polarization is a quantum mechanical characteristic, we can present it as two photons, like this, and this photon goes freely through wave plate, and this photon experiences the delay, and if we have a half wave plate, the delay is the half of wavelength. And if you remember the graph of the sine function, you understand that the delay of half length is the same thing as multiplication on -1. So this photon here reflects here. And we have on the exit of the wave plate, this photon reflected along this fast axis. So this multiplication by -1 is exactly the same thing which we have in our quantum oracle in the states like this.